Hi everyone, welcome back to this course of Introduction to Statistical Mechanics of Soft and Active Matter Systems. So, in the last class, we talked about the random walk, 1D random walk, where there is a reflecting boundary. So, today we will continue the discussions and recap of the past discussion was so basically, earlier it was what was the probability of finding that worker at position M after n steps. Now, what we have done is that we have introduced a reflecting barrier at M is equal to M1, a special site or special point. Okay, and we will also assume that this reflecting boundary is at a positive axis. Let's say M1 greater than 0. Now, how to sort of interpret the whole thing is that uh, is that how you are going to tackle the problem. So to tackle the problem is that so whenever the particle will arrive at this specified positions m1, and it will in the next step it will reach to a step m1 minus 1 with a probability 1. Okay, so that is the term reflecting boundary means. Okay, now our job is to find the probability w m n given m1. That means probability of finding that worker at position m after n steps given that the reflective boundary is at m1. Okay, so now to sort of understand the problem, it is easier or it is convenient to see the displacements or the how it takes its steps in mn plane. Mn means in at one axis there will be the number of steps or the what is the step number you are taking right now, or the current step number, and m is what is the position of the worker. Okay, so to do that, now in that plane what will be the the way to represent it, since n is the number of steps you are at which step you are in, and m is the positions you are in right now. So at one step and next step it will go. So for since n is increasing at each step, so n will be along this positive y axis, and m can be positive x axis and negative x axis in both directions. So basically from one position it can go diagonally like this or this. Okay, with time forwarding, right? So and so this is the thing, that the representative point in this nm plane that will move upward by 1 unit, while at the same time it will suffer some lateral displacement which is for these positions of this worker either in positive or negative directions. So that's why this is diagonally like this, because so we can see here. So for that we have drawn a certain graph, or I will come back to that later. Now when there is no reflecting boundary at m is equal to m1, the probability of reaching at position m after n steps is wmn, that we have done for the free random walk. Now when a path reaching m is done by n reflections, there it must be counted 2 to the power n times, since at each reflection it has probability unity of retracing its steps. Because if it is gone here, then so just a minute, I lost my. Okay, so basically what we are trying to do here is that since there is reflection, that means after the each reflection it can come back to this 2 times, right? Let's say from here to here, because to go here, let's say to go m at let's say, so to understand these things, you understand like this. Let's say at t equal to at time equal to t time, you are in at m1 steps. So that means at t minus 1 you were at m1 minus 1, and since there is reflecting boundary at t plus 1, you will be again at m1 minus 1. So that trajectory for one reflection, this will be like you are revisiting m1 minus 1 path two times. Again, if it is happening again, reflection is happening one more time, it will visit two more times. So that means it will be, multiplied like this. So 2 times 2 times 2, so n reflections means, so 2 reflections means 2 times 2, that's equal to 4. 3 reflections means 2 times 2 times 2, that means 8, so 2 to the power 3. So at that way, so there will be 2 to the power n times you have to count that each reflections. Okay, so now what we have done is that we can take that relevant factors by adding to the free probability whether there is no reflections, okay, plus the probability of 2 to the power m1 minus mn, where 2 to the power 2m1 minus m is the image point after n steps. So to understand that, what we will do is, here let's say a particle starts from here, so it reflects at point E, so and it goes point D after the reflection. So after n steps it goes to D, since because of this reflecting conditions. So basically, if there was no boundary, so you can think of it as, let's say you take the image of every point around this plane M1. So this point will be represented by this point will be represented by this point will be represented by this. So these are not dotted line, means these are not real trajectories, these are like imaginary trajectories. So basically you will get that if there was no reflection, it should go to D prime. So basically what we can do to sort of map the random walk with reflecting boundaries to random walk without reflecting boundaries like this. So if there was no boundary, it must have been to this D prime positions. So you can see there is a symmetric symmetric property around this M1 line. Okay, so we can, since there is a reflections, so why it is happening? It is happening because when you are introducing a reflecting line, that means you are by hand increasing the probability of finding that walker at position M or position at M. So you are increasing that probability, that means you are increasing the number of trajectories that is going to M compared to the event where there is no reflecting boundary. Now you can, so since the probability is increasing, that means number of trajectories, possible trajectories, or number of possible sequences that we have counted for free step, compared to that, here the number of sequences will be much more, right? So to account that, what we have done, so we have added this probability, which is W of 2m1 minus m. Why is that 2m1 minus m? Because let's say this yellow lines depicts this m1 point, so you have to find the probability of finding this m. So the image point of this m will be this one. So this distance is m1 minus m. So since this is reflection, so this distance will also be m1 minus m, and this point is m1, so m1 plus m1 minus m, that's why it is becoming 2m1 minus m. So now to get the whole number of trajectories where there is a reflecting boundary at m1, where we have adding extra term which is like that, that what is the probability of particle, what is the probability of that random walker, occur going to this position 2m1 minus m after n steps. So if we add this sequence along with this sequence, then we can get the total number of trajectories, and from that the probability. Okay, so that is what we have done. Okay, so now basically what we have done is it's like this, right? Okay, so now this Wmn m1 will be this term. This is because there is a free random walk, 1D random walk. So now that position is now additional to that, we are adding one more term, is this one, right? Just a minute, I'm just changing this. This will be the whole thing. So basically your problem becomes, so basically what we are happening, so to incorporate the reflecting boundary at m is equal to m1, we are basically increasing the number of trajectories where the random walker reaches m1, sorry, m, and so how it compared to the case where there is no reflecting boundary wall. Now since you are increasing, since number of trajectories are increasing, that means the probability of finding the walker at m also increases. Okay, so basically how much it will increase? It will increase, so basically you can add those trajectories for free random walks where it reaches the point 2m1 minus m after in steps. So that is what we have done here. So this term, this is a constant, this is, so we have derived that what is the probability. So here we have determined what is the probability here, what is the probability of finding the worker at position M after n steps we have done. So this is the probability expression. Now this is the position M. Now if we take the position 2 M1 minus M, then this guy, this M guy will be changed, right? So that will be 2 M1 minus M. That's what we have done here. We have just changed it. So this is a prefactor, so this will be common. So this is for probability of finding at position M, and this is the term for probability of finding at position 2 M1 minus M. So now if we use the net displacement, which is x is equal to ml, L is the step length. So you take a certain step length, let's say the step length is 3 millimeter, whatever it is, a constant, okay, because we have taken it constant as the variable. So now we are changing the variable from m to x, okay, and consider the probability of finding the worker at position x at time t. So we have got, what is the t? T is time, total time. T is the, here we have done it. So t, let's say, so here the particle suffers n displacement per unit time. So then t will be capital N by small n, right? So t will be, so t is capital N by small n, right? What is the total amount of time it takes to reach n steps? Since in small n is the number of steps per unit time, so to reach n steps it will require small t amount of time. So now we need to calculate the probability of this, where that the particle is between x and x plus delta x, where delta x is greater than, very greater than L. Okay, so after a time t during which it took n number of steps in the presence of reflecting boundary. So now also the reflecting boundary we are just changing to x1, like the position, where we are just multiplying with this L. Now similarly here also, using the previous expressions like this, 1 by 2 pi dt exponential of minus x square 4 dt times delta x, here x square will be x1 square, right? So that we have done here. So this is x1 square, sorry, this will be x1 minus x, so x1 minus x square, but this term prefactor will be same. Now according to these equations, what we will find is at, if you take dwx at x is equal to x1, we will get, when we will make it 0, then we can get it, because because there the probability of finding the particle must be 0, right? So this is what we have done here. Okay, so today we will next do one more thing, that is, let's say there is an absorbing wall at m equal to m1, equal to m1. So the absorbing, so let us assume there is a, let's assume there is a perfectly absorbing barrier at m equal to m1. Okay, now how we can, so so whenever you deal with the statistical mechanics in software and estimator systems or any kind of statistical mechanics problems, so that actually requires a certain skill or certain sort of tweaking of the problem, because sometimes the problem seems different, but to solve it easily you have to interpret it differently. Okay, so basically what we will do here, so the interposition for this problem will be interposition of the perfect absorber at m equal to m1 means that whenever the particle arrives at m1, it vanishes. So absorbing means there will be no further displacements, right? So it does not have any further capabilities of performing further displacements. Sure. Now this kind of problems has various applications in different things. It may be sounding very simple now, but you can see different physical problems that is eventually becoming this kind of random walk with absorbing wall. So the actually the uh, main capabilities or the main insights that physicists give, they sort of find this kind of similarities between in a physical problem, and they can apply this kind of statistical tools or statistical methodologies to that problem, so they can get the relevant solution. Okay, so now further discuss. So now we got two important questions that we should answer, like two important questions regarding this. Okay, so what are those two important questions is that what is the analog of this problem that we have considered so far. So first, probability that the particle or the walker arrives at m, and m must be less or equal to m1 after taking n steps, after taking n steps, that is the first thing. And second is that what is the average rate, the average rate at which the worker will deposit itself on the absorbing wall. Now if we get answer of these two questions, then sort of we can handle it pretty well. Okay, so first probability, let's say first situation. Okay, for the first situation, that probability WMN, so it does mean that what is the probability of reaching, the worker reaches M after n steps, giving that there is absorbing condition at M1, that is number of counting, oh again, so the counting number of counting the number of, okay, basically you are counting the number of distinct sequences of steps which lead to M. So here we should be careful to exclude any sequences where it can arrives at M1, because you remember, if you arrive at M1 you get stuck there, there is no further displacement. Okay, so careful to exclude all sequences which include even a single arrival to M1. So that means if we first count, if we first count all the possible sequences which lead to M in the absence of absorbing wall, and then if we should exclude a certain number of forbidden sequences, why it is forbidden? Because it shouldn't reach M1, then we should get all those probability. So let me write in black color that in basically, let's say basically you count all the possible sequences sequences which lead to aim in the absence of the absorbing wall, and then you should exclude exclude a certain number of forbidden sequences. Okay. Now there is another thing happens. So every such forbidden sequences uniquely defines other sequences which leading to the image point that we have done for the reflecting boundary case on the line in the MN plane, right? And conversely it is also true. So also you can say that also for every such forbidden sequence there is a unique sequence obviously corresponding to this, that that leads to 2m1 minus m point, which is, let's say, the image point of m, image point of m on the line m equal to m1 in the MN plane. Okay, so now for by reflecting with respect to the line m is equal to m1, the part of a forbidden trajectory, the part of a forbidden trajectory above above its last point of contact with the line m is equal to m1 before arriving at m, we should be led to a trajectory leading to this image point, leading to the image point. Similarly, for every trajectory which leads to 2m1 minus m, we should or we necessarily should obtain by reflection a forbidden trajectory leading to m like this. So if any trajectory is reaching to m, let's say there is no but there is a free case, no absorbing case, because we have to map the whole things with respect to the free case, because we know about the free trajectories. Now to get, so we should avoid those trajectories which sort of touches or crosses the m1 line. So basically to do that, what we have also, we can write image point like this, and conversely you can say for every trajectory which leads to 2m1 minus m, we necessarily obtain by reflection of a forbidden trajectory leading to m. That means, because why it is happening, because any trajectory leading to 2m1 minus m must necessarily cross the line m1 equal to m. So it is because any trajectory leading to 2m1 minus m must necessarily cross the line m is equal to m1, right? So then what we have to done, what we have to do. So for the reflection cases, we were sort of increasing the trajectories to the number of trajectories possible, but here for the absorbing case we have to decrease the number of trajectory, because if it reaches M1 or if it crosses M1, then those trajectories shouldn't be counted. Okay, so there the probability will be lesser. So here you will write, so basically I will explain with a nice so here Mn, given that this is at M1, this is basically calculating those trajectory which are free minus those trajectories which are reaching to 2m1 minus m after n. So basically from here you will get this. Okay. Now if you do that, then for large n, for large n or t tends to infinity, you can write W m n m1 is equal to 2 by pi n to the power half into, so probability of this is exponential of minus m square by 2n, and minus probability of this is minus exponential of minus 2m1 minus m whole square divided by 2n. So this is the another thing. Now we can sort of change it to these things. Okay, so basically what we have done, so let's see this example. Okay, so let's say in this problem it touches this thing. Okay, so up until point this, so this trajectory shouldn't be considered. Similarly, there can be some trajectory which you know should reach this from this point d prime and touch this e. So we need to sort of minus those trajectories. So basically by saying what we are trying to say here, that so first we should calculate all the possible trajectories, any possible trajectories that should reach at m after n steps. Then we are neglecting, or we are sort of removing those trajectories which are forbidden, right? Now those forbidden sequence means, so those forbidden sequence, there should be an unique sequence that should leads to 2m1 minus m, which is a image point of m in the m1 plane, right? Because let's say here, let's use another color. So let's say it goes like this. Okay, that, so here it reaches to this, right? That means, so, and let's say now it reaches this point. That means if data was not there, then basically what would happen is this point. So 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 basically now this trajectory should be forbidden because it touches this line. Now if we assume that after touching, if it is not touching like this, then we can get a trajectory like this. Let's say that should lead to 2m1 minus m. So we could get those trajectory that should reach 2m1 minus m after touching m1 once. Okay, so by this way we are neglecting this term. So basically from here if we change it to x and t, then let's say this, if we get x as ml and t as capital N by small n, then w of xt given that x1 at x1 positions, that should be 1 upon 2 of 2 times pi dt. This is a similar thing, and exponential of minus x squared by 4 dt. Right, now you have to minus, you have to subtract that probability that is due to reaching at this position, reaching as these positions, where this is 2x1 minus x whole square by 4 dt. So basically you are sort of neglecting this thing. So sorry, not neglecting, you are subtracting this thing. Okay, now according to these equations, if you put in this equation, if you put, so according to this equation 3, now if we put w xt x1 at x is equal to x1, that should give 0. Let's say if you put here x1, this is also x1, that should give 0. So that is the meaning of the boundary condition of absorbing boundary condition, which is basically the meaning of absorbing wall, where the finding probability of the worker becomes 0. So you can check it also here. So here it will be, let's say this is a constant, let's say this is c, so c times x as equal to x1, so put it exponential of minus x1 square by 4 dt minus exponential of minus 2x1 minus x, that will be also x1 whole square but 4 dt. So that becomes c times exponential of minus x1 square by 4 dt minus exponential of minus 2x1 minus x1, this is x1 square by 4 dt, basically that will make 0. So this is the meaning of the absorbing boundary conditions. Okay, so now we have to find another question, which is the meaning of what is the rate at which it should reach this position. So now our next question, our next query concerns the probable rate at which the particle or the worker, the particle deposits 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 itself on the absorbing screen. Let's formulate the problem specifically. Okay, so basically our main query to know the probability A at M1 n, which is reaching at position M1 after n step, after taking n steps. So that means the particle, what is the probability that particle will arrive at M1 without ever having touched or crossed the line m equal to m1. So first time appearing at this position m1, okay, at any earlier step. So people also relate it with first passage time. In fact, this is the first passage time. So what is first passage time? First passage time is what is the time, or what is the earliest time it touches the this any position, certain position. Here the position is specified by the absorbing wall. Basically we are also calculating that thing, that probability of a particle arriving at M1 without having touched or crossed the line in earlier steps. So first thing first, that was basically there, n should be odd or even, depending upon whether M1 is odd or even. So if M1 is odd, n should be odd. If M1 is even, n should be even. So now let us assume suppose there is no absorbing skin, suppose there is no absorbing wall. That means if there is no absorbing wall, that means it is free case. For free case, if it is has to reach M1, then its earlier step must be either M1 minus 1 or M1 plus 1. That is true, right? Because it can only hop one previous point. So it should be either its previous point must be M1 or M1 plus 1. So its position at n minus 1 step must be either on M1 minus 1 or M1 plus 1. Now, every trajectory that is arriving from this point to this point, that is forbidden, because it cannot cross this point, because we have write this right without ever having touched or crossed the line m is equal to m1. So that means every trajectory, every every trajectory every trajectory that arrives at m1 equal to m1 at nth step from m1 plus 1 n minus 1 is a forbidden one. Okay, in the presence of in the presence of absorbing screen. Okay, because why this is because those trajectories because those trajectories must have crossed the line m1. But one thing is that it is just talking about the previous step, but it does not say that it will be uh, reaching. So it does not say that if certain particle or certain worker is coming from from m1 minus 1, that is also allowed, because it so happened that earlier times, although it is at m1 minus 1 at n minus 1 step, but it at earliest times it must have crossed or touched that m1 once. So basically we should have been more careful to count all those allowed trajectories. That is the you know most insightful thing here. Okay, so alert it does not it does not follow that all trajectories all trajectories arriving all trajectories arriving arriving at m1 n from m1 minus 1 n minus 1 are permitted ones. That may not be also true. For a certain number of trajectories that may touch or cross the line m is equal to m1 earlier than its last step, that is also possible. So those the number of such trajectories which arrives at m1 minus 1 at n minus 1 by touching or crossing the line m equals to m1 earlier than this time step earlier than its last step is actually, if you see, is equal is equal equal to those equal to those arriving arriving at m1 plus 1 n minus 1. That should be the same thing, right? Because if those trajectories should be equal to 1, because this, like if this is m1, this point and this point, m1 minus 1 and m1 plus 1, they are just reflective points. That's why this is equal to those arriving at m at this point. So by reflection argument for the above statement is that is that by reflection by reflection about the line m is equal to m1, we can uniquely derive from a trajectory leading to m1 plus 1 n minus 1, another leading to m1 plus 1, sorry, m1 minus 1 n1 minus 1, right? We can actually uniquely derive from a trajectory, right? Because if all these things are like reflection to this point, so we can get those things. Okay, which has forbidden parts, forbidden character, character, and conversely it's also true, conversely it's also true. So thus we can write therefore therefore the number of permitted ways of arriving at m1 for the first time after n steps is equal to all the possible all the possible ways of arriving at m1 after n steps in the absence of the absorbing wall, absence of the absorbing wall minus twice the number of ways of arriving at m1 plus 1 n minus 1, again in the absence of in the absence of the absorbing skin or absorbing wall. So basically we are neglecting those trajectories. So from here you can easily write, so that will be, first what is the probability of finding at this point, that will be n factorial n minus m1 by 2, that factorial times n plus m1 by 2, that factorial, right. So reaching at m1 minus 2 times n minus 1, because we are just talking about the earlier step, n minus 1 steps, reaching where n plus m1 by 2 factorial minus n1 n minus m1 minus 2 by 2 factorial, because if it is at m1, so the total displacement will be, because it is taking n minus 1 steps, so that is why it is happening like this. Okay, how it is happening, just a little bit calculations if you know. So n left, let's say something, n right is something, so total nl plus nr, nl plus nr is n minus 1, and nl minus nr is m1, m1 plus n, sorry, m1 plus n, and if you do this, then you can get nl is n plus m1 by 2, whereas, sorry, this will be nr, this will be nr is this, and nl will be how much, nr minus n minus 1, so n plus m1 by 2 minus n minus 1 plus minus 1, so that makes it n minus m1 minus 2 by 2. So that is what we are doing here. Okay, so let's say, let's keep it like this. So from here you can get, this is the number of ways. So let make it, so this was the equation number 3, so let's say this is equation number 4. Okay, so if it is equation number 4, then you can do some algebra to write it as n factorial divided by n minus m1 by 2 factorial, and n plus m1 factorial can be written like this. So from here you can take out, it is common, and if you take n plus m1 by 2 factorial common, then it becomes 1 minus n minus m1, because if you product it with n minus m1, then it will be like this, right, n minus m1 by 2 by n. So here if you times it with n, you have to time with divided by n, here this is 2, and to get it to this n minus m1, you have to again write it as n minus m1, right, because n minus m1 by 2 plus 1, that is n minus m1 by 2. So this is the algebra. So basically we have multiplied these terms n and these terms n minus m1 by 2. So if it is multiplied by n minus m1 by 2, then there will be 2 by n minus m1, right. So That is what we have done. Okay, so basically, so if you multiply it n minus m1 by 2, then it will be n minus m1 by 2 factorial, and here you have to also n minus m1 by 2 you have to multiply here in this point. So from here you can get this. Let's say this is also equation number 5, and from here you can easily get m1 by n n factorial n minus m1 by 2 factorial n plus m1 by 2 factorial. Okay, so then required probability will be required probability probability a m1 n is then given by a m1 n is equal to m1 by n times w by m1 times n. So this is the our crux of this study. If you get this, now we have to take the limiting case, and what will be the case for n tends to infinity. So for large, for the limiting case, for the limiting case of large n, we can write as a m1 n is equal to m1 by n 2 by pi n to the power half exponential of minus m1 square by 2n. This is equation number 7. Okay. Okay, so now we need to change to x. So if we further write, then if we further write as x1 is equal to m1 times l, and number of steps n is equal to nt, and also d, which we will later see, this is a diffusion coefficient, as nl square. Then we can write, so l is the length of each step. Then we can write that a of x1 t is, so if you multiply with l, this will be l also. So here you can also write then x1 by nt, x1 by nt by 2 by pi dt to the power half, then exponential of minus xn square by 4 dt. This kind of equations will become again in the diffusion equation. So please remember this form. Now finally, if you are asked the following questions, that finally, let's say, now if we if we ask the probability the probability q x1 t delta t. What is this? This is basically the what is the probability the particle arrives arrives at x1 during t and t plus delta t for the first time, then we can write q of x1 t is equal to half of a x1 t in delta t. Okay, so this is question number 9. Now this equation is actually is the number which arrive at x1 position in the time taken to traverse the two steps, right? Because there is two steps is there, t and t plus delta t. So equation 9 is basically is the number is the number which arrive at x1 in the time taken to traverse the traverse two steps two steps. Okay, thus you can easily write that q x1 t is equal to x1 t times 2 2 into pi dt times half exponential of minus xn square divided by 4 dt. Okay. Okay, so this is equation number 10. So basically, how can we interpret these equations? Now, to interpret these equations, we need to understand the following thing. Okay. So, to interpret it, to interpret equation 10, we can write that it gives it gives the fraction of a large number of particles initially at x is equal to 0 and which are deposited on this absorbing wall, on the absorbing wall, which is per unit time at time t. So at time t, what is the number of particles which starts from x equal to 0 and deposited at the absorbing wall? So we also can say, we also can verify the fact that qxt qx1 t verifies this relation d of dw dx x is equal to x1 must be this, where w is defined as this equation number 3, where w is defined as equation 3, and it has a interesting, interpretations that we will see in the next, discussions, what is the these things. But we can check, right? What was w? W was x t, was, let me copy this equation, this one. So this is c, uh, only variable this one. So we can sort of copy it, copy. So we have copied it here. So basically, if wxt is like this, okay, so then what will be dwx? So then dwx, c as it is, c, this is the constant. So exponential of minus x square by 4 dt, that becomes minus x square, that means minus 2x by 4 dt exponential of minus x square by 4 dt, and this becomes minus minus plus 2 into 2x1 minus x by 4 dt exponential of minus 2x1 minus x whole square by 4 dt. Right? Now if you substitute dw dx at x is equal to x1, so basically it becomes c as it is, x1 means minus 2x1 by 4 dt exponential of minus xn square 4 dt plus 1x1, 1x1's cancelled out, and this becomes 2x1 by 4 dt times exponential of exponential of, oh, so there is a minus sign, so we need to take it as minus 2x1 minus x whole square by 4 dt. So this will be 1x1, so this will be x1, this will be x1 square by 4 dt. Yes, I have done some mistakes because of this thing. So for this it will be minus. So this will be minus because exponential this because there is one minus sign here. So minus of minus will be minus one more minus. Okay, so we can see then this becomes minus c x1 by 4 dt times 4 into exponential of minus xn square by 4 dt, and c value is this. So if you substitute this, then this becomes c was 1 by 2 pi dt. So this 1, this becomes 4 cancels out, so this becomes c becomes 1 by 2 pi dt. So 1 by 1 by 2 pi dt half into x1 by dt times exponential of minus x1 square 4 dt. Right, so what was q? Q was x1 by t 2 times this. So there is only one this thing missing. So you can easily write this as 1 by d. Uh, did I do something miss? Oh, there is a minus sign. So minus 1 by d, and this term 1 by 2 pi dt, this x1 by t exponential of minus xn square by 4 dt. So this term, basically if you just look at this term and this term, these are the similar. So this is qx1t, so this is qx1t. So from here you can easily write qx1t becomes minus d dw delta x delta w delta x at x equal to x1. So basically from here you can get that if you take the gradient of the probability and if you multiply with this constant, then you can get this rate. What is the particles that actually starts from x equal to 0 and actually deposited at this wall per unit time. Okay, so I hope that you understood these things, and basically we will connect all these things to the diffusion equation and all these other things when when we will discuss this the Fokker-Planck equations and all these things. And so think about it, and we'll again meet in the next class. So I'm stopping here.